Okay, today we're going to look at some trig identities. We're going to continue. First of all, we're going to define an identity. So an identity is an equation that is true for all values. That is true for all values. So for example, x plus x equals 2x. No matter what value I put in for x, it's always true. X squared equals x times x. No matter what x values I put in, it's always true. How about like 2 times x plus 4 equals 2x plus 8. This is an identity because it's always true. You actually can tell if an equation is an identity if you solve for x and you end up with 0 equals 0. So if I do like 2x plus 8 equals 2x plus 8, and I subtract off the 2 x's, and I subtract off the 8, I get 0 equals 0. That doesn't seem to make sense, but what it tells me is I have an identity. Okay, so let's continue. Actually, let me just bring up another point. You can tell if something has no solution if you get a false statement. For example, and once again, diversion, 2x plus 5 equals 2x minus 3. So you go through the algebraic root, you're like, fine, subtract 2x off both sides, and subtract 5 off both sides, and you get 0 equals negative 8. Because you have a false statement, there's no solution. So 0 equals, a false statement, no solution. 0 equals 0, an identity. Good. Okay, let's take a look at the first identity. So the first set of identities are, I'm going to erase this. The first set of identities are the Pythagorean identities. Let's see. Pythagorean identities. Okay, so what we did was, if you recall in the last couple of videos, we actually put the unit circle on the grid. So if it's a unit circle, that means, that's 1. And so the idea is we try to correspond, we use like SOHCAHTOA, right? And so we created a triangle, okay? And we looked at the first thing we did was we looked at this side over here, and we saw, you know what? That's cosine. So the cosine of theta, and this is theta in here, is the adjacent over the hypotenuse. But in this case, the hypotenuse is 1, so it's simply the adjacent. And this side is cosine. Now, what about the other side? The height of the triangle, right? Well, that's kind of sine. Sine of theta is the opposite over the hypotenuse. Well, because the hypotenuse is 1, this side is sine. Now, we know from Pythagoras' theorem that we have, sine squared plus cosine squared equals 1. And this is our first identity. And you'll see that no matter what you put in. So if you go in your calculator, now, quick thing, this is a notation. Once again, sine squared theta, that represents sine of theta squared. So on the side, if I ask you to evaluate sine squared of 30 degrees, what this means is, what this represents is actually the sine of 30 squared. It's just notation. It's notation. Square it, so it's 1/2 squared or 1/4. So this is the first identity. Yes, that's the first identity. And what we can do is just manipulate it around. What's another idea? Good. Now, so for example, if I say, the sine squared of 73 degrees plus sine squared of cosine squared of 73 degrees, if you see that, you say, what? And I don't give you a calculator, you say, well, how do I do that? But you immediately recognize that this is a Pythagorean identity and this equals Nice. Good. Now, we can use this. This shows up, they like these. So this shows up in some exercises. So we're going to use to find unknown variables. Using to find unknown values. Okay, and so let's look at the first one. Question number 1. If the sine of A is equal to 2/3 and A is in the quadrant 1, find cosine of A and tangent of A. So when you have problems like this, you have a couple of options. We're going to start with the algebraic solution. Even though I'm a big proponent of geometry, we're going to start with the algebraic solution. So we have sine of A, and we're looking for cosine of A, and you say, oh, you know what, Mr. Adler? I have this identity here, sine squared, because I'm lazy, and you know what? I don't want to do this today. Sine squared of A plus cosine squared of A equals 1. So I have 2/3 squared plus cosine squared equals 1. Cosine squared equals 1 minus 4/9, which is 5/9. Cosine of A is equal to plus or minus the square root of 5/3. But what do you think? Is it both of them? Well, because this is the first quadrant and cosine is positive in the first, the answer is radical 5/3. Now, the next part asks for tangent. Well, we can talk about another identity that we came up with. And we know that the tangent of A is actually equal to the sine of A over the cosine of A. So, we have the sine of A, which is 2/3. We have the cosine of A, which is radical 5/3, which works out nicely to 2 over radical 5. You can rationalize it if you want. I don't care. Is it positive or negative? Well, it's positive because tangent is also positive in the first. Okay, let's move on to another example. Example 2, I'm going to say it out loud and then I'm going to erase it. The cosine of B is 4/5, and B is in the fourth quadrant. Find the sine of A and the tangent of A. So let's see. While I'm putting this on the board, you can kind of start it. Let's see. So we know example 2, we have the cosine of B is equal to 4/5. B is in quadrant 4. Find sine of B and tangent of B. So once again, you can use the algebraic method again. You can say, you know, Mr. Adler, fine. Sine squared of B plus cosine squared of B is equal to 1. I have sine squared plus 4/5 squared equals 1. Sine squared equals 1 minus 16/25, which is 3/5. So, I'm sorry, 9/25. Therefore, sine of B is equal to plus or minus 3/5 because we're taking the square root of 9/25. But you say, Mr. Adler, we're in quadrant 4, so the answer is negative 3/5. What's going on with the tangent? Same thing. The tangent of B, we know the tangent is sine over cosine, so we know it's negative 3/5 over 4/5, which is negative 3/4. We know this is correct because we know the tangents. Sorry, it's sloppy. The tangent is negative in the fourth, so the answer should be negative. Is there a faster way to do this? Well, geometrically, it's probably your best bet to do this a little faster. So if we write the triangle, here's a fourth degree rotation. So B is in the fourth quadrant. I'm going to drop a triangle, an altitude. I know that the cosine is 4 over 5, adjacent over hypotenuse. What is the length of this third side? Well, you might say, well, it's 3, Mr. Adler. I know that because, it's a Pythagorean triplet, 3, 4, 5. But please remember, it is negative 3 because this is a directed distance. So the negative 3 just refers to going down, and that helps you find, the sine. So quickly, we're done. So you can use the algebra, or you can quickly create a geometric sketch. And so we know that the sine is opposite over hypotenuse, and the tangent is opposite over adjacent. And that's up to you. Let's use the geometric to do the third, to do the next problem. Let's see. Let me erase this. The sine of C is negative 5 over 13, and C is in quadrant 3. Find the cosine of the tangents. So let's see. Question number 3. We have the sine of C is equal to negative 5 over 13, and C is in quadrant 3. So the question is, find cosine of C and tangent of C. Now, I like the visual for this one. So let's get a triangle, because I see 5 and 13, and once again I'm like, oh, that's another Pythagorean triplet, 5, 12, 13. But let's get the visual to explore this idea of directed distance. Directed distance. So let's see. So we have a rotation, and it's in the third quadrant. We know that sine is negative in the third, we know that cosine is negative in the third, and we know that tangent is positive in the third. We draw a triangle, right? Okay. We're told that the sine of C is negative 5 over 13. What's going on with the other length? Because I need to find the cosine, I need that adjacent. Well, I already know the Pythagorean triplet is 5, 12, 13, but what's going on here? Well, this is negative 12, because once again, it's also a directed distance. In geometry, to the left and down is negative. To the right and up, it's positive. So let's see if we can connect this. The cosine of C is adjacent over hypotenuse, negative 12 over 13. And once again, you could have used your algebra. Once again, I love my algebra, but I think I like I equally like my geometry, and it comes in handy, and it's easier to work with sometimes. What's going on with the tangent of C? Well, the tangent is opposite over adjacent, but look what happens. Negative 5 over negative 12, 5 over 12, it's positive, because tangent is positive in the third. Nice. Let's move on to, you know what? Let's take a break, and then I'll come back in a second. Okay, let's resume the video. The next thing we're going to talk about for the IB exam is double angle identities. There's a lot more identities, but a higher level has to do that. You guys don't have to do it at central level, but I am going to put up the video if you want to know all the rest of the trigonometry. So a double angle, we want to figure out what the sine of 2x is, and the cosine of 2x, and the tangents of 2x. These show up, they're important. They're kind of, they show up. So the question is, how do we find the formula for the sine of 2x? Well, what we're going to do is, once again, you don't have to derive this, and you get these in the formula books, but I want to show you where it kind of comes from, or one way. So I'd like you to draw an isosceles triangle. So let's call this side P and P. And let's drop an altitude whose height is h, and the base is now bisected r and r. And let's call this x and x. Okay. So my first question to you guys is, find the area of the large triangle. And so you'd say, okay, Mr. Rather, well, it's 1/2 p squared sine of 2x. So we have the 2x. Now, what I'd like you to do is I want you to find the area of both those little triangles. So the area of the small triangle is what? So we have, let's see, it's 1/2 ph sine of x, but because there's two of them, okay, good. Now, we can say that because the two small triangles make up the big triangle, so I can say, okay, 1/2 p squared sine of 2x is equal to ph sine of x, right? Yeah. Now, I'm going to solve for 2x. So let's see. We have sine of 2x is equal to, how do I get rid of the half? Multiplied by 2. How do I get rid of p squared? Divided by p squared. Sine of x. Okay. Well, let's see what's going on here. Well, the p goes out with the p. H over p is what? Well, h over p is actually, that's the cosine, right? Because the cosine of x is equal to adjacent over hypotenuse. And I substitute that here, and I get this really nifty identity, 2 sine of x, cosine of x. That's kind of cool. You're going to need that. It's going to show up. So for example, they're going to say, actually, you know what? Yeah, so they're going to say, if the sine of d equals 3/5, find the sine of 2d. And you're going to say, no problem, Mr. Adler. Because if I have the sine, and let's say that d is in the first quadrant, is in quadrant 1, you're going to say no problem. To find sine of d, I need to find the sine and the cosine. That's no big deal, because I know from my diagram, if this is 3 and 5, this other side is 4. Therefore, the cosine of d is 4/5, and therefore the sine of 2d is equal to 2 times 3/5 times 4/5, which is 24/25. Nice. The next identity we need to find is the cosine of 2 theta. And we can actually use the same diagram, right? Let's see, can we use the same diagram for it? Yeah. What do you think? Well, let's see what we have here. Well, what is the cosine? Well, we have 3 sides. We're going to use the cosine rule. So if we want to find the cosine of 2x, that's our goal. We're going to use the cosine rule. And if you recall the cosine rule, remember it was like c squared equals a squared plus b squared minus 2ab cosine c. So in this case, we're going to say, you can look that up. If you recall, remember it was like c squared equals a squared plus b squared minus 2ab cosine c. Once again, you have the 3 sides and the included angle. So let's use that with this diagram. Let me erase this to give them more space. Let's see, what do we have here? What do we have here? Let's see. We know that we have 2r squared is equal to p squared plus p squared minus 2p squared cosine of 2x. Once again, please review the cosine rule, and you'll see where I got this from. Let's see what's going on here. Well, I need my cosine, so let's see if we can combine this. Let's see what we have here. So we have let's see, 4r squared equals 2p squared minus 2p squared cosine of 2x. Can I divide anything out? Yeah, I can take the 2 out. 2r squared minus p squared equals p squared minus p squared cosine 2 of x. What do you think? Well, I think I want to divide everything by p squared. I think I'd like to divide everything by p squared. So, well, what happens? Well, let's see. This is 1 minus cosine of 2x. What's going on here? Well, r over p is actually sine of x, right? The sine of x is equal to r over p. So this actually is 2 sine squared x. And it turns out if we manipulate this around a little bit, we get the identity that the cosine of 2x is equal to 1 minus 2 sine squared of x. This is our first, this is another identity. You get the formula for it, you're not going to be asked to derive this. This is just one way. There's 100 ways on the internet. What you notice in your formula booklet, you're going to notice in your formula booklet that there's 3 formulas. Where do they come from? Well, let's take a look at that one. Hold on one second. Sine of x. Sine of x can be replaced by 1 minus cosine squared, right? So we have 1 minus 2 plus 2 cosine squared. The second identity is 2 cosine squared theta minus 1, right? And then, but you said, where's the third one come from, Mr. Adler? Well, let's figure that out also. Let's see what we have here. Well, let's see. Well, if we have the cosine of 2 theta, 2x, is equal to 2 cosine squared minus 1, but 1 was equal to sine squared plus cosine squared, we actually end up with the third identity, which is cosine squared theta x minus sine squared x. And these are the 3 identities you can use to solve these problems. Let's see, here's the first one, here's the second one, here's the third one. It's up to you. You can use any one you want. So let's go back to the last problem we just solved, which said we had, the last problem is that the sine of d was equal to 4 over 5, and d was in quadrant 1. I asked you to find sine of 2s. Now we can find cosine of 2d. And we have 4 formulas. So we knew that cosine 2d, we can use either of these 3 formulas. It's up to you. Maybe I want to use the first one. So it equals 1 over 2 times 4 over 5 squared, which is equal to 1 minus 16 over 25, 32 over 25, and that's negative 7 over 25. Someone might say, Fatima might say, hey, Mr. Adler, I'd like to use the second one. Okay, well, we know the second one, if the sine was 4 over 5, the cosine of d was 3 over 5. Fatima wants to use the second one. So d times 3 over 5 squared minus 1, which is 9 over 25, 18 over 25 minus 25 over 25 equals negative 7 over 25. And maybe Evan says, Mr. Adler, I want to use the third identity. Because Evan has to use the third identity. Fine, Evan. Be that way. Cosine of 2x is, let's see, what do we have for cosine? 4 over 5 squared minus, 3 over 5 squared minus 4 over 5 squared equals 9 over 25 minus 16 over 25. that also gives us -7/25. So you can use the three identities. The last thing is the tangent. How do we find the tangent of 2x for this problem? Well, some of you were saying, well, that's easy, and you know what it is, because the tangent of 2x is simply the sine of 2x over the cosine, 2x over 2x. So in this case, the tangent of d is simply the sine of d, which was what? 4/5. No, I apologize. The tangent of 2d is the sine of 2d over the cosine of 2d. What were the answers? Let's see. What was the sine of 2d? Oh, it was 24/25. And what was the cosine of 2d? Well, we did it 3 times. -7/25. Final answer, -24/7. You might say, oh, wait a minute, that's over 1. That doesn't work for tangent. Can be anything. Tangent has no restrictions on its range. Sine and cosine are restricted by -1 and 1 on its range. But tangent doesn't have a restriction on its range, and that's basically it.